Welcome to the second part for your iLearning day, if you're in the 2026 spring course, in case I reuse these videos. What I wanted to highlight specifically was the intermediate value theorem. So this is like the last lesson in Unit 1. Typically don't assess on it because it runs right up into the Unit 1 summative, but you will need this theorem to make justifications, to prove things in future problems. It's surprising how often this theorem arises. And what's really nice about intermediate value theorem, what I think is nice, is it's fairly intuitive. If you can kind of break away from the math terminology and definition and just kind of focus on what it's saying. And so what I'm going to do is just instead of kind of going through the exact example in my notes, if you're looking at the 1.9 notes, I've really just kind of sketched a graph up here, and we're starting with this hypothesis, like this if piece. F is continuous, so I've got some kind of function that is continuous. So I've got no break from point A to point B. We're able to sketch it from one point to the next without picking up my pencil. That means no holes, no jumps, no vertical asymptotes, none of those types of discontinuities. From A to B, where if I was to plot the points, their y values would not be the same. And so that's what the f of A not equal to f of B is referring to. So for example, let's say I was to put A here, so let's just let A represent a negative value. And let's say its y value, f of A, is here. So I'm going to go ahead and put a point. So this point would just be A, f of A, if I was to list out the coordinate. And I'm going to put B somewhere off to the right, because typically it's A, then B, in terms of how we read it. And I'm going to place this point a little bit higher, so I'm going to put it here, because again, f of B can't be the same as f of A. And so I've got a second point here, point A, point B. And I know that I have a function connecting these 2 points, and I know that my function has to be continuous. Remember, that's the beginning standpoint. We can't have a not continuous here. So like if you were to sit here and after I do this go, well, what if it was discontinuous? You're right, if it's discontinuous, this whole thing breaks. So remember that we're starting with this idea that I have to be able to draw a continuous function from here to here. Being continuous function means I also can't kind of overlap itself. So as I draw, I have to constantly go up. Now I can go up and down, but I can't like overlap. It's still got to be a function. So I'm just going to draw a line. The most basic would be linear. I'm going to draw something a little bit more curved, just to kind of give it more of a interesting shape. But let's say this is my function for f. Now what intermediate value theorem says is that if I know that this function is continuous, if I know that I have to be able to sketch this from here to here without picking up my pencil, then notice that between this y value and this y value, I have to hit it at some point. So if this y value was, say, 2, and this y value was, say, 10, if f is going from here to here, I know I have to hit every y value in between 2 and 10 at least once. At least once. Because I'm continuous. There's no way to skip it. Because if I was able to skip one of these y values, then I have a discontinuity. But I can't have a discontinuity. The whole thing is continuous. That's why I was kind of emphasizing that so much. So what the intermediate value theorem says is that if I have this set up, then my function hits every middle value or intermediate value in between A and B. You have to. And so what it'll say is it'll say something like n is a number between f of A and f of B. Right, so n represents the y value. And then its final conclusion will say then there exists at least one C value. At least one C value in between A and B that f of C equals n. In other words, if I want to ask the question, is it possible for this function to have a y value of 4? The answer is always yes, and in my graph it happens here. There's my C. C is the x-coordinate. The x-coordinate always describes location. So when I'm looking at this theorem and it's saying, okay, there exists at least one point, we want to know where. right? Where is it located? Because I know the y value already, what it's worth. So we're trying to figure out, okay, is there a possible location that this happens? And if so, let's find it. And this again is called the intermediate value theorem. The first example that I have for you in 1.9, when it's talking about a car and it's stopping, it's the idea that if you're hitting on the brakes after traveling 65 miles per hour, your car is going to hit every single possible speed that it can until you get to zero. Now there's no speed that you can skip, because when you're traveling continuous. Your car just can't magically teleport, right? There is no quantum physics here right now, and quantum teleportation. So intermediate value theorem is really, really important if we want to justify or prove that a function can hit a certain value, because as long as I can show that it's continuous, then it works. For example, if you take a look at example 3, the table above gives gives values of a function g at selected values of x. Which of the following statements is true? Statements, if true, would be sufficient to conclude that there exists a number c in the interval 0 to 7 such that g of c is equal to 50. Now if you're looking at the table, you've got x coordinates of 0, 1, 3, and 7. And then you have y values 24, 35, 42, and 68. In other words, notice that 50 as a y value would sit somewhere in between 42 and 68. But our function could also hit 50 at any other point, because I only have those moments in time. So what we would need to just show that if I want it to be possible to hit 50, is I just need to show that my function's continuous. And if you look at your Roman numeral 3 letters, it's the last one. The condition that's necessary would be g is continuous for all x in the interval. Because if g is continuous, then I have to hit every y value between 24 and 68. That's 50 included. G is increasing wouldn't be enough, because we could still skip 50. I can draw a graph that's increasing at 50. It could be a vertical asymptote, and then it just keeps increasing on the other side, a y value. So I guess that wouldn't really work. So I guess you would need a jump, right? It gets to 50, open circle, and then keeps going. Define for all x in the interval might also not be true, because I could have a filled in dot, and again, skipping 50. It goes up to 49, and then it starts back at 51. Still defined at every x value, but I don't hit that y value. Continuity is the key. Continuity is the key. Example number 2, show that there is a root between 1 and 2 for the equation. So that's x is 1 and x is 2. This one, I'm going to challenge you to kind of take a look at. And the way that I'm going to kind of help you with this one, because it's something we will kind of take a look at a little bit more later on, is the word root means 0 or x-intercept. So what this question is really asking is that when you look at this function, between x is 1 and x is 2, I want to know, is there a place where this crosses the x-axis? Well, think about it. If I want to show that there's a y value of 0 in between these two, one way to show that is that from 1 to 2, this point is below the x-axis and this point is above. Then if f is continuous, I have to cross at least once. Or vice versa. If f of 1 is above and f of 2 is below, then I would have to cross the x-axis at least once to determine that c value. So here, show that there is a root between 1 and 2. 1, you need to talk about how a cubic is continuous. And then 2, you just need to show that at these two endpoints, one sits above and one sits below. And if you do that, then there has to be an answer between those two things. And you can find it graphically, algebraically, you could solve for it as well if you want to try it. But that is the intermediate value theorem. Hopefully that makes sense. If not, please let me know. I'd be more than happy to work with you outside of class in terms of tutorial. Same thing when it came to the other limit problem. But intermediate value theorem really means what it says. If you've got a function that's continuous from this point to this point, then I can hit every y value in between. I have to. There's got to be some x value that is associated with it. Intermediate value theorem.